Hi, thanks for joining. Please make sure you subscribe to follow us on all the various platforms here on the podcast, as well as on YouTube. The stuff we write on Substack, as well as quick takes on Instagram and on Threads. If you're enjoying what we're putting out there, please make sure you're sharing with all your friends and family. And if you have questions or comments about the stuff we're putting out there, please make sure you leave them in comments to us. We'd be more than happy to cover them in future talks. As we get into the festive months, as we get into the holidays, we tend to have large family meals. We tend to have large gatherings with large amounts of food, where undoubtedly we might jokingly talk about the idea of food coma and suffering from food comas after having such large meals. And we tend to hear a whole bunch of claims about what's causing the food coma, or we may joke about having certain types of foods that are going to cause that food coma. But what is causing the food coma? What is making us have that sleepiness following such large meals? Food comas. Let's talk about that.
Warning. The following presentation contains information that might contradict what you have previously heard, or believed to be true, about how the human body works, and contains material that is not suitable for closed-minded individuals. Enjoy.
When we start talking about and discussing food comas, a lot of jokes come about as it relates to, oh, I've had so much tryptophan in my turkey that I am going to get sleepy. That is one of the more common thought causes for food comas. But what are the kind of rationales that we might have that might make it true or not? Here are some of the more commonly held beliefs that people have as to what is going to be the cause for food comas. It's from having too much sugar in the meal. It's from having insulin spikes. It's from having too much fat or salt or too much protein in the meal. It's because blood is shifting away from the brain into the gut because we've had so much food. Or, like I just stated, it's from all that wonderful tryptophan that we see within the turkeys. Let's go ahead and let's talk about each one of these possible causes for the food coma and whether or not it's actually physiologically possible for them to cause that food coma. So let's start with the idea of too much sugar in the meal causing the food coma. The idea that too much sugar in the meal is going to cause the food coma stems from experimental results in lab organisms that exhibited lethargy following excessive consumption of carbohydrates in their meal. The issue with this is that the idea is responding to eating large meals of carbohydrates for humans can't be separated from changes in insulin levels, a topic we're going to get to in a little bit. Moreover, there is other statements attributed to sugar levels and the activities in humans following eating sugar that doesn't correspond with the idea of lethargy. That is the quote unquote sugar high, the sugar hyperactivity, which is also a misconception about sugar in the meal. However, there is some credence to the idea that sugar consumption is linked with increased activity. It's not that this link is what we see within the sports beverages or within the endurance packets that we might see from the stores or in advertisements related to these ideas, or what we might see in most of the pre-workout or competition meals that we might have as relates to carbohydrate loading. But if we actually get into the idea of how we go about eating large amounts of sugar and coming about getting the food coma, it's not going to be corresponding. The metabolism of our body runs on carbohydrates. We will always be using carbohydrates for fuel sources, regardless of what type of diet that we are following, even those who religiously follow a ketogenic diet. We will be readily using all of the carbohydrates that we are consuming within a meal, or we will be storing them for later points in time. When we start looking at this idea about sugar in the meal and causing the lethargy or causing the food coma, what we're really looking at is we're looking at a dose response. And the problem is that we don't see a dose response from large carbohydrate meals for us, similar to what we see within the lab organisms, mainly because of the amount that's being fed to the lab organisms relative to the amount that we would actually be consuming. So taking in the amount of time that we consume the meal, as well as the amount of carbohydrate being consumed within most of the meals, we are not getting a large enough bolus, a large enough amount of carbohydrates to have the necessary effect that we would see coming out of the lab studies looking at lab organisms. The other thing we have to look at is the time dose response. And when we start looking at the time dose response, we have to look at what is the relative amount of body mass to the amount of carbohydrates being consumed based on the duration of consumption. As there tends to be greater dosing of carbohydrates from many of the drinks that we regularly consume, but we don't attribute food coma to that carbohydrate load in a lot of the drinks that we consume. taken during the duration that we are consuming the large bolus of or the large amount of carbohydrates in the drinks that we're consuming tend to be excessively short, which means that we're getting a rather large dose in a very short window of time that should be causing the food coma, but doesn't cause the food coma. So if we start looking at this idea about the duration of food consumption with this large carbohydrate meal, it doesn't line up with the idea that carbohydrates is causing that idea of food coma or is leading to the food coma that we might exhibit, especially if we start looking at the addition of a lot of the stimulants that we might see in the beverages that we're going to consume, in particular the caffeine that we might have within a lot of the beverages. Which takes us to the next idea that a lot of people offer that goes hand in hand with the idea about sugar in the meals or carbohydrates in the meals, and that is the spiking of insulin following the food. The idea about sugar inducing food coma is off because it ignores the necessity for insulin to act to help, quote unquote, clear the excess sugar from the blood. While excessive consumption of glucose or sucrose, table sugar, more than 1 to 1.2 grams per kilogram of body weight per hour in a meal causes excessive increases of insulin to be released during a meal and after a meal. The idea about consuming this large amount of carbohydrates within the meal leading to the spike in insulin, both during and after the meals, as well as sporadically throughout the day, independent of eating foods that we're going to consume that have large amounts of sugar, doesn't line up with when we're going to see that food coma kind of set in. The release of insulin is triggered by a host of factors beyond just the sugar in the meals. Simply eating meals is going to cause insulin to release. Thinking about eating meals is going to cause insulin to be released because insulin is one of the hormones that's going to be involved with the regulation of feeding, the regulation of feeling full, the regulation of wanting food based off of swings and shifts in the insulin signaling pathways that we have throughout the day. But we tend to simply focus on insulin as relates to the sugar, as opposed to insulin as relates to all the other things. Having that in mind, having said that, the production and release of insulin is regulated by an interaction of a host of factors. The first interaction that we look at when it comes to the meal is the interaction between the taste buds in our mouth and the foods that we're eating. The taste buds in the mouth is going to start sending a signaling to our brain, and from our brain, we're going to send secondary signals out that is going to start to prime the pancreas to release the insulin in response to feeding. We have very similar types of receptors that exist within the veins of the intestines or around the intestines that are taking all of the nutrients that have been digested and absorbed and move them from the intestines through the liver and then out into circulation. When those receptors sense high carb, a signal gets sent to the pancreas that says, okay, all of that insulin you've been primed to produce from tasting stuff in the foods, from the taste buds, is time now to go ahead and release that insulin. It's also time to start to think about starting to produce more insulin. As the blood with the high glucose, with the high carbohydrates, filters through the pancreas, additional cells within the pancreas start to sense this high levels of glucose, high levels of carbohydrates in the body, in circulation. And it says, okay, pancreas, go ahead and do even more release of insulin, even more insulin production. And this is where we start getting this insulin spike. And here's the thing, it happens within about 25 to 35 minutes of eating. The spike in insulin is delayed from the meal by about a half hour, and it goes away over the next 30 to 40 minutes. That is when we start having that clearance of glucose. With the completion of the clearance of glucose within 2 hours of consuming the meal, where we start to see a tapering of insulin over those 2 hours. Which means that if insulin is the culprit for the food coma, it would set in about 40 minutes after a meal and be done within the next hour because the insulin levels would have slowly dropped off. And that's not typical of the food coma in terms of the food coma timeline. There is a caveat that we have to point to here, and that is that for a lot of the tissues, insulin is not going to be the primary reason for glucose to get into the cells. We only see this insulin action at 3 particular tissues: the liver, the skeletal muscles, and the adipose tissue. Now, there's another caveat that we have to look at here, and that is for those that are insulin dependent diabetics. The inappropriate timed injection of insulin can cause a hypoglycemic event. That hypoglycemic event may cause lethargy, but that's not food coma. That is a hypoglycemic lethargy. And it should be seen as an independent thing. And we usually treat this hypoglycemic lethargy by simply consuming sugar or giving that person a sugar thing to eat. And that's going to counter effect the hypoglycemia. That counter effect of hypoglycemia causing the person to become energetic, causing the person to lose lethargy, is going to be one of the counter arguments that we can make towards this high sugar meal or the effect that insulin was going to have as it relates to the high sugar or high carbohydrate meal that's being consumed. So, yes, we might see a dropping of blood glucose levels over an hour or so following meals due to the effects of insulin, but that's not going to cause such a drop in blood glucose levels to cause hypoglycemia or cause hypoglycemic lethargy. So we know that it's not going to be from the sugars. We know it's not going to be from the insulin. So what else might be a culprit in terms of causing that food coma to come about? The next idea kind of deals with or goes into the idea about how bliss and bliss point can impact my overall emotional state and can cause me to feel more relaxed. And by causing me to feel more relaxed, can put me into an easier state to get into food coma. And that is there's too much salt, too much fat, too much protein in the meal that's causing me to go into the food coma. Physiologically, there's no real rationale of why salt would be listed with all of these ideas about things that could cause food coma. Salting food or causing excessive amounts of umami within the foods might lead to an extra bliss point that can cause additional consumption of food, which could lead to food coma, which we'll talk about as we go through the progression within this point here. But it's not really salt. Salting food and absorption of salt will lead to increased fluid absorption because water follows salt into the body. But by itself or in combination with fats and proteins, salt would not lead to the lethargic feeling that we get after a meal, which leaves those other two ideas here, fats and proteins. The first thing that we have to look at here is related to the time and duration that is required for the digestion of fats and proteins within the intestines. In general, it takes much longer to digest the proteins into their smaller absorbable molecules, the amino acids, than either fats or carbohydrates. Not only does it take longer, but it requires additional metabolic activity in order to digest the proteins. This increased metabolic activity is one of the hypotheses that's being offered to explain why we have a lethargic state following high protein meals, as well as the quote unquote meat sweats that some might get when they consume excessively high animal protein meals. Yet, the amount of increased metabolic activity is not enough in itself to trigger metabolic fatigue that would cause you to fall into a food coma. Similarly, the fat digestion, there is increased metabolic activity in the digestion of fats, which includes second digestion and metabolism by our liver following absorption. Yet, just like the digestion of proteins, the increased metabolic rates associated with the digestion of fats is not enough to cause metabolic fatigue or lethargy. Additionally, the time frame for digestion of proteins and fats being at least 60 to 90 minutes would mean that we're looking at 2 to 3 hours after a meal before we start having the onset of food coma, should it even be possible for this increased metabolic activity to cause metabolic fatigue and cause food coma. The other point is related to the idea about taste and bliss causing the relaxation to occur. When we talk about bliss, what we're talking about is we're talking about the psychological reward that we get for consuming things that we enjoy consuming. When we taste things that we enjoy tasting. Foods that have high fat, high salt, high protein, high sugar tend to induce taste sensations that we find rewarding. One such thing or one such taste that we might have from having high fat, high salt, high protein is the taste sensation umami. We tend to find umami rewarding and pleasurable as it causes a change in the sensations within the mouth, within the taste buds, within all the receptors within the mouth that we have being triggered when we eat. This change in sensation, this change in neural activity, puts us into a state of relaxation while we're eating. This state of relaxation comes from that bliss and it's very short lived. It typically does not cause widespread relaxation throughout the whole entire body for any extended periods of time. And will typically end when the ideas around the bliss also end, when we stop experiencing bliss. Not only will we lose that sense of relaxation when the bliss ends, but we're going to enter into a state of agitation, seeking out the next point of bliss because we're trying to get a reward. It's the idea of seeking out a reward that is going to cause us to want to eat additional things that draw out that bliss sensation. Additionally, not everyone will experience a bliss response with the same type of food or at the same levels of the different types of nutrients that we have within the food, whether it is fats or proteins or sugars. This is how we get food preferences. This is how people have personal preferences for foods, whether those foods be sweet foods or salty foods or crunchy foods or fatty foods. All of this will cause us to have to think about what is our favorite foods and how those favorite foods impact my sense of bliss around the foods. Anytime we even think about our foods or our favorite foods, we start to enter into a state of agitation, a state of cognitive agitation, where we want to go and find that food in order to alleviate that reward seeking behavior, that need to get a fix in our reward center, in our bliss center. Just thinking about your favorites is going to do this. If you think about your favorite types of food and kind of start making mouth movements as if you're chewing that food, you're going to get a cognitive agitation wanting to get more of that food. And so if we think about the high fat, high protein, high salt meals that we're consuming, yes, they may put us into a bliss point if we like fatty, salty foods. But if we don't like fatty, salty foods, it's not going to put us into a bliss point. If we're eating large amounts of sweet things, if we happen to have a sweet bliss point, it's going to put us into bliss. But those blisses, that idea of relaxation coming away from the meal due to the exhibiting of bliss, is excessively short-lived. It's not going to put us into that state of tiredness that we usually associate with the food coma. Which takes us to the next ideas, which looks at the digestion and the changes physiologically, anatomically that take place with digestion. And that is, I'm going to have blood move to different areas of the body because of the fact that I'm eating large amounts of food and having large amounts of digestion taking place. And this idea is that we're having a shift in blood to the gut. The idea goes like this. If blood flow is going to shift to my gut for digestion and absorption of the food that I just ate, that means I'm going to have a drop of blood or a reduction in blood flow to other areas of my body, in particular my brain. While there is a drop in blood flow that will occur throughout the body, we do not see drops in blood flow going to the brain during periods of consumption or during any other period where we might see a cardiac shift. That is a directional change in flow of the blood through the body. Very rarely are we going to see a drop in blood flow going to the brain. Blood flow going to the brain tends to be constant. We will actually see an increase in blood flow going to the brain during periods of consumption as well as during periods of exertion when we're actually being very active. So this idea is sound in terms of the idea that, yes, we're going to have a shift in blood flow. But that shift in blood flow is not going to be at the expense of the brain. It's going to be at the expense of the skeletal muscles. It's going to be at the expense of the skin, where we're going to shift blood away from the skeletal muscle, away from the skin, and towards the gut, so that we're able to have this increased amount of digestion, this increased amount of absorption, where we're going to move that blood around because we're going to have higher metabolic activity in these areas relative to what we would see in the skeletal muscles or in the skin during the periods of eating, digestion, and absorption. So yes, the cardiac shift is going to take place. But the cardiac shift is the drop in blood not to the brain, but to the other areas of the body that are not going to be working during the time of the meal. So we can't use this shift in blood flow to help explain food coma. It's not from the change in blood flow away from the skeletal muscles to the gut, and we definitely do not see a drop in blood flow going to the brain. So we'll eliminate that one from the options. The other option that is typically given, and is one that we hear over and over and over and over again, is that the turkey that we're going to have has tryptophan in it, and tryptophan is going to cause us to become sleepy. Too much tryptophan is one of the principal causes that everybody likes to cite when it comes to the food coma. But why? Why is it so commonly cited as a reason? The principal reason that tryptophan is being cited is that tryptophan, an amino acid, is going to be metabolized by some of the neurons within our brain to form a neurotransmitter, the chemical messenger that the neurons send to each other to change activity, into a molecule known as serotonin. Serotonin 5-hydroxytryptamine. 5-hydroxytryptamine. It comes from tryptophan in terms of the way in which the neurotransmitter is developed. This neurotransmitter is an inhibitory neurotransmitter. That means it's going to slow down the rate of activity within the neurons, in particular the neurons within the brain. And by slowing down the rate of activity within the neurons, the idea is that it's going to reduce the level of arousal that I'm going to have, the willingness to stay awake. The other chemical that can come about from tryptophan is a neural hormone or a hormone that is made by the pineal gland known as melatonin. Melatonin, along with serotonin and a couple other neurotransmitters, are going to be involved with the regulation of sleep and wake, what some people will call the circadian rhythm, but physiologically is the circadian regulation, the quote unquote biological clock for sleeping and waking. When melatonin levels are high, we tend to be very sleepy, we tend to go to sleep. When melatonin levels are low, we tend to be awake. And that's because melatonin is going to act on the neurons to reduce neural activity by blocking signals of neurotransmitters that are excitatory, that are going to cause the neurons to increase their activity. When we combine the two signals of serotonin and melatonin, we have this idea that since both of them are going to be coming from tryptophan, if I have large amounts of tryptophan, that must mean that it's the cause for the sleepiness. The problem is it's a post hoc agero prepare hoc fallacy. Because it happened last, it must be the cause. There's not enough time in between when we consume the turkey meat to the onset of food coma to say it's from the tryptophan. While tryptophan is found in turkey meat, approximately 300 milligrams for every 4-ounce serving, and other poultry might also exhibit tryptophan, there is not enough tryptophan being consumed, nor enough time between the consumption of the meal and the onset of the food coma to allow for the protein to be digested, the amino acids to be absorbed, the amino acids to be transported to the neurons and to the pineal gland, and then converted into either serotonin or melatonin to cause the food coma. To eat enough turkey to generate a spike in tryptophan to cause a spike in serotonin and melatonin without causing toxicity, you're looking at needing to eat somewhere in the neighborhood of 40 to 64 ounces of turkey. That is 2.5 to 4 pounds of turkey. Additionally, the assumption being made is that any and all tryptophan that is being consumed is only going to go to the production of serotonin and melatonin, which it does not. Just like every other amino acid that is being absorbed following the breakdown of proteins that we are consuming, the amino acids will be delivered throughout the body to every cell. And any cell that can use tryptophan will use the tryptophan. Tryptophan will be embedded into a host of proteins that are being generated by all the cells within the body, independent of the conversion of tryptophan to melatonin or to serotonin in certain select cells. And then the release of melatonin and serotonin must not be inhibited by any other signals that will act as an antagonist to the melatonin or to the serotonin signaling that would then cause me to go into food coma. So, if all of these reasons are not correct, what is the actual cause for the food coma? Why is it that I feel very tired after eating large meals? If it's not because of the spikes in insulin, if it's not because of having so much sugar in the foods that's going to cause the additional spike in insulin? Why is if it's not from having too much fat or too much protein that's causing an excessive amount of metabolic activity to digest down those things? If it's not from the change in blood flow to the gut outside away from the other metabolically active tissues. What is the cause for it? We know it's not the tryptophan because of the timeline. We know that it's not the insulin because of the timeline. We know it's not the sugars because of all the effects that sugar has in terms of metabolic activity. So what's the cause? What's actually causing the food coma? This is where we have to take a step back and think about what are the physiological and neurophysiological responses that we see surrounding the want to eat and the not want to eat. The want to eat and not want to eat is based off of hormonal and neurotransmitter signals that are attempting to balance the signals of eating and stop eating based off of fuel utilization and necessity for nutrients in order to maintain normal homeostatic balance within our metabolism. These signals correspond with other signals at the hypothalamus and within the hindbrain in order to trigger changes in metabolism, changes in metabolic activity, changes in circulating levels of hormones that will either drive behaviors towards getting food or drive behaviors away from getting food. Whenever we eat, there is a hormone and neurotransmitter response that causes us to either start eating or stop eating. It's those neurotransmitters and hormonal responses that are going to be the root cause for the food coma to set in. During normal balance, we have signals where we get hungry. And those signals for getting hungry include an elevation of ghrelin, an elevation of glucagon, a reduction in insulin, a reduction in leptin, a reduction in GLP-1, a reduction in PYY, just to name a few hormones. Those hormones trigger from the hypothalamus a change in neurohormonal signals from neuropeptide Y, which causes an activation on the dopaminergic pathway within the brain to cause us to either get food or cause us to start eating. We can independently bypass this because of higher cortical things, higher cortical areas where the desire to want food will drive me to get food, even if I don't have the physiological signals, the hormonal signals that I need to eat. On the opposite end, if we are fed, if we are satiated, we get a swing in hormones where we get an increase in PYY, we get an increase in GLP-1, we get an increase in leptin, we get an increase in insulin, we get a reduction in ghrelin, we get a reduction in glucagon, just to name a few. What that swing in hormones do is it triggers the hypothalamus to cause a different hormonal pathway to start, the POMC pathway. And what the POMC pathway is going to do is it's going to instigate an increase in serotonin, a reduction in dopamine within the serotonergic and dopaminergic pathways within the brain. That's going to cause me to stop eating by blocking the signals to start eating. We can bypass this signal with higher cortical functions with thinking, I don't want any more food. And that's because the entire pathway is corresponding or correlating or coordinating signals in between higher brain areas, the hypothalamus, and the hindbrain in such a way to direct feeding behaviors, direct gastrointestinal functions, and direct my fuel utilization, what everybody thinks about in terms of the energy balance. This whole pathway is balanced and coordinated through a host of neuroendocrine and hormonal signals and neurohormonal signals, which includes the endocannabinoidal system that is going to lead to either greater food consumption or less food consumption based off of activation of leptin and ghrelin receptors within areas of the hypothalamus. When I start to have large amounts of food, when I start to have excessive amounts of the I'm no longer hungry signals, when that pathway gets activated more than what it should, what does it happen? I go past from the I'm full signal and move into the I am tired signals. And so what ends up happening? When I become excessively satiated, PYY, oxyntomodulin, GLP-1, leptin, insulin, all go sky high. We have a drastic reduction in ghrelin, glucagon, and other counter-regulatory hormones, which includes epinephrine and cortisol. This is going to stimulate an area within the hypothalamus to start the POMC pathway. The POMC pathway is going to start by inhibiting the dopaminergic pathway, which is going to say you've gotten your reward. And it's going to stimulate the serotonin pathway to trigger us to stop eating. What this does is this is also going to start to change our energetic pathways. So we stop trying to get food. It's also going to put me into a state of relaxation. That state of relaxation comes about due to changes in melatonin and endorphin levels. It puts me into a restful state. It's that restful state when I have excessively high POMC levels, leading to excessively high melatonin levels, leading to excessively high beta endorphin levels, that puts my whole entire mind into a state of ease. When I'm in that state of ease, I become completely relaxed. That relaxation is going to allow me to have the time and effort to continue the digestion process and continue the absorption process and continue the process of disposing, putting the nutrients where the nutrients need to go within the body. That is why food coma comes about. It's this balance point where we go too far past the stop eating side of the signals, where rest becomes the necessity to take place. This change in overall activity is the food coma. It's that need for rest following excessively large meals. It's important to understand that the shifts is not about food or the type of food. It's about the neurotransmitter changes due to hormone changes that come about from the food we're eating. Once again, it's not about the amount of food or the type of food or a lot of the other things that we like to discuss as it relates to the cause for food coma. It's entirely about the shift in the hypothalamus and the limbic system's regulation of the level of neurotransmitters, dopamine causing excitation, serotonin causing inhibition, along with other inhibitory signals, in particular gamma aminobutyric acid, GABA, and melatonin. The GABA and melatonin, along with the serotonin, put me into that state of relaxation within the brain. When we experience this change from the hypothalamus to cause the elevations to take place, we get this reduced want to be active. We stop being active and we start being restful. Given the appropriate environment and the appropriate environmental cues, it will lead to a feeling of tiredness, and that feeling of tiredness is what's going to lead to the food coma. So, food coma is the change in brain activity that comes about that leads us to feeling extra relaxed. It's the change that comes from elevated levels of endorphins, elevated levels of serotonin, elevated levels of melatonin that occur in response to the hormone shifts that happen following excessively large meals. It's not coming from spikes in insulin. It's not coming from large amounts of fatty, salty, or sugary foods or high amounts of protein within the meal that we're eating. If anything, we can stipulate that the food coma can arise from overconsumption of the comfort foods that we might have during the festive times, not the specific nutrients that we might see within those foods. And that's simply because the comfort foods put us at a higher level of easement. It's the higher level of easement that will lead us to a state of restfulness. It's that state of restfulness that's going to lead to the food coma that can come about from the foods that we're eating, not the types of foods that are being eaten. The comfort food that we see within the holiday meals leads to the food coma, not the type of food in terms of the saltiness or the sugariness or the proteins or the fat that might be there. Which leads to the obvious question: is there a way that we can go about preventing the food coma? Well, if you listen to all of the talking heads about this, they would say eat smaller meals. Time your meals correctly. Consume caffeine or other stimulants with your meal that will have a antagonistic effect to the signals that would cause food coma. But in reality, the only way to prevent food coma is not to consume so much food in a single meal to elicit the additional signaling of POMC to cause higher amounts of serotonin, higher amounts of endorphins, and higher amounts of melatonin to be released. This can only occur by eating smaller portions within a meal and allowing time for the short loop, that is the I'm full signals, to kick in and stop you from overeating. Being realistic, this bit of advice might not be tenable, which means to prevent the food coma might also require needing to make an environment that does not allow you to have increased levels of relaxation to set in immediately following the large meals. This means we shouldn't be consuming our meals immediately before sitting on our couch, sitting in our favorite chair, and watching television. Or we might want to look at ways to shift our activity into something that would keep the brain activity high and away from wanting to go to sleep, or shift the brain away from sleepy time based off of the idea that melatonin, serotonin, and endorphin levels are going to have an impact on that sleepiness, which means that if we can shift our brain away from that sleepy time signals immediately following large meals, we can offset some of the signals that could cause food coma. Taken as a whole, food coma is something that we can maybe prevent, but it becomes very problematic to prevent based off of the fact that we have very limited control around the holidays and around the holiday meals and the environment that we might have to go to. Well, thanks for listening. Hopefully you got a bit out of the conversation here as it relates to food coma and the causes for food coma. If you have other topics you'd like us to cover, please make sure you're leaving those for us in the comments. If you're enjoying the topics that we're covering, please make sure you give us that big thumbs up, that like, share it with all your friends and family. If you have other topics you'd like us to cover, please make sure you're leaving for us in the comments. Please follow us here on the podcast as well as on YouTube, the written stuff in Substack, as well as the quick takes on Instagram and on Threads. Stay tuned for future conversations and future discussions about the myths and misconceptions we have about the human body and how we can go about using our scientific understanding to live a healthier life.